When you look into a clear night sky, you're not just seeing distance, you're seeing time. Starlight takes years to cross space, and the farther we look, the older the light becomes. The most ancient light is stretched by the expansion of the universe, shifting from the energetic blue of youth into the deep infrared. Our eyes can't see those wavelengths, and most telescopes glow too warmly to measure them. The James Webb Space Telescope was built to solve that problem. Webb's entire design, its mirror, its orbit, its temperature, exists to catch the universe's oldest, faintest glow. Webb's mirror is 6.5 meters wide, a honeycomb of gold-coated beryllium segments polished to nanometer precision. Gold is not just pretty, it reflects infrared efficiently, which is where ancient light now lives. After launch, Webb unfolded this segmented mirror in space and focused it to act as a single surface. The observatory sits about 1 million miles from Earth at a gravitationally stable point called L2. There, a 5-layer sunshield, roughly the size of a tennis court, keeps the telescope in permanent shade. In that cold, instruments can quiet their own thermal glow and listen for photons that began their journey more than 13 billion years ago. Temperature is everything for infrared astronomy. Webb's detectors live only a few dozen degrees above absolute zero. One instrument, the mid-infrared instrument, is chilled even further by a cryocooler to just a handful of kelvins. Why so cold? Any warm surface radiates infrared light. If the telescope were warm, it would swamp its own measurements. By pushing the instrument temperatures down, engineers lowered that background to near silence, letting the cosmos speak clearly. Now consider the target. The first galaxies formed a few 100 million years after the Big Bang, when the universe was young, small, and filled with neutral hydrogen. That gas absorbs ultraviolet light below a sharp threshold called the Lyman limit. As ancient starlight crossed the swelling universe, every wavelength stretched. The once ultraviolet light slid redward into Webb's infrared bands. This redshift doesn't mean galaxies flew away through space like rockets. It reflects space itself expanding, carrying light with it like ripples on a growing pond. Measuring that stretching tells us not only how far a galaxy is, but when in cosmic history its light set out. Webb's near-infrared camera, NIRCAM, is the wide-field workhorse that begins the hunt. It photographs the same field in several filters at once, capturing short and long infrared images simultaneously. In those stacks, faint red smudges appear, tiny, compact, and often invisible in the bluer filters. That vanishing act is a clue called a dropout. Neutral hydrogen blocks the bluer side of a young galaxy's spectrum. If an object disappears in blue filters but shows up in red and infrared, it may be extremely distant. However, imaging alone can't prove it. Confirmation comes from spectroscopy. Webb's near-infrared spectrograph, NIRSPEC, spreads each galaxy's light into a rainbow and looks for fingerprints, the sharp hydrogen cutoff and bright emission lines from gas excited by newborn stars. NIRSPEC uses an array of about 250,000 tiny shutters, each thinner than a hair, to observe hundreds of targets at once. When the positions of these spectral features match the predictions of physics after accounting for redshift, astronomers can tag the galaxy with a precise distance. That's how faint smudges turn into timestamps from the early universe. Within its first deep surveys, Webb found galaxies whose light left when the universe was less than 350 million years old. Some are no wider than a few hundred parsecs, smaller than giant star-forming regions inside the Milky Way. Yet they shine fiercely. At first glance, a few seem too bright for their age, almost overgrown. Follow-up spectra and improved models show a subtler truth. Early star formation was likely bursty. Short, intense episodes produced many massive, hot stars at once, temporarily boosting brightness before supernova winds blew gas out and the galaxy calmed. That stop-and-go rhythm explains how compact systems can punch far above their weight so early in time. If these bursts shaped the first galaxies, then Webb is not just cataloging light, it is watching fireworks from the universe's youth. Bursts explain brightness, but they also explain violence. Each generation of hot stars ended quickly, some exploding as supernovae after only a few million years. The blasts stirred surrounding gas, created shock waves, and seeded the environment with the first heavier elements beyond hydrogen and helium. Those heavy elements, carbon, oxygen, iron, would later form planets and living chemistry. So every faint smudge in Webb's deep images is not just a galaxy. It is a forge where cosmic history's raw ingredients were first created. Astronomers knew from older telescopes that early galaxies must have played a role in transforming the universe from opaque to transparent. For the first few 100 million years after the Big Bang, neutral hydrogen absorbed and scattered most ultraviolet light, creating a fog that hid distant sources. At some point, that fog lifted in a process called reionization. Ultraviolet photons stripped electrons from hydrogen atoms, making the gas transparent. Webb's ability to see galaxies during this transition helps scientists trace when and how reionization unfolded. It appears not as a single event, but as overlapping bubbles around star-forming galaxies that grew and merged until most of the cosmos was clear. Evidence for those bubbles comes from a subtle line in hydrogen called Lyman alpha. Neutral hydrogen should block this line, yet Webb and ground-based observatories detect it from very distant galaxies. The most likely explanation is that galaxies carved out ionized neighborhoods where Lyman alpha could escape. As more galaxies lit up, more bubbles overlapped, and the fog retreated. This patchy clearing fits with models of reionization driven by many small sources rather than a few giant ones. In other words, cosmic dawn was messy and local before it became global. Webb's role in this story is both statistical and personal. On the statistical side, surveys count how many galaxies appear at each redshift, how bright they are, and how quickly their numbers grow. Those counts feed into cosmic star formation rates, which reveal how energetically matter was turning into light. On the personal side, Webb dissects individual galaxies with spectra, finding not just distances, but details: gas composition, star temperatures, even the presence of dust. The combination lets astronomers ask whether the early universe was uniformly efficient at making stars or if it varied wildly from place to place. Variation seems to be the rule. Some galaxies formed stars in steady trickles, others in bursts. Some were relatively dusty even at young ages, which means supernovae were already enriching their gas. A few hosted active black holes at their centers, where gas spiraled inward and released enormous energy. The presence of those black holes so early challenges models of growth. How could they reach millions of solar masses within a few 100 million years? Webb's spectra are starting to tease apart which light comes from stars and which from accreting black holes, hinting that both shaped early galaxies. One striking fact often overlooked is how small these galaxies really are. A typical early galaxy might be only a few thousand light-years across, tiny compared to the Milky Way's 100,000. Yet they were hotbeds of activity, with star formation rates per unit mass far higher than today's galaxies. The early universe was not gentle. It was efficient, fast, and chaotic. The contrast between their small size and outsized impact underscores how quickly complexity can arise once gravity and gas begin their dance. To appreciate why Webb's discoveries were so surprising, it helps to recall what came before. The Hubble Space Telescope captured the deepest visible light images ever taken, the famous Hubble Ultra Deep Field. Those pictures revealed thousands of faint galaxies, but only out to a certain distance. Beyond redshift 8 or 9, their light had stretched into the infrared, slipping beyond Hubble's reach. Hubble offered hints of early galaxies, but confirmation was elusive. Webb's infrared vision extended that frontier, and suddenly, the hints turned into entire populations. Galaxies at redshifts of 10, 11, even 13 have now been spectroscopically confirmed, representing times when the universe was less than 400 million years old. What shocks astronomers is not just their existence, but their brightness. Several candidates initially appeared to be as massive as the Milky Way, yet existing only a few 100 million years after the Big Bang. That seemed impossible under standard models, where galaxies grow gradually by merging and accreting gas. Later refinements reduced some of those extreme estimates, but the message remained. Galaxies formed stars far more rapidly than expected. Either the early universe was especially good at making stars, or our models underestimated just how chaotic and efficient the first bursts of formation could be. Consider the role of massive stars. The earliest stellar generations, sometimes called Population 3, were predicted to be far more massive than most stars today, some reaching hundreds of solar masses. They lived only briefly, burning furiously hot, producing torrents of ultraviolet light, and exploding as supernovae that seeded their surroundings with the first heavy elements. Webb cannot directly resolve individual stars at that distance, but its spectra show chemical fingerprints, like elevated oxygen or carbon, that point to enrichment from earlier generations. That means even in these faint smudges, we're seeing the aftermath of stars that no telescope will ever witness directly. It's also worth noting how Webb's sensitivity changes the game. In one deep field, a single image may capture galaxies across nearly the entire age of the universe. The nearby ones show mature spirals with dust lanes and bars. The distant ones are tiny red dots representing the first stirrings of structure. Each pixel contains a different chapter of cosmic history, stacked together by distance. By parsing them, astronomers can reconstruct how galaxies transformed from chaotic bursts to ordered systems like our own. And hidden within those pixels may be signatures of black holes. Even the smallest early galaxies may have hosted them. Gas swirling into a black hole releases intense radiation across the spectrum. Webb's spectra are now distinguishing whether a galaxy's light comes purely from stars or whether part of it is powered by a central black hole. That distinction matters because black holes accelerate reionization. Their ultraviolet radiation can be even more potent than stellar light. If many small galaxies housed feeding black holes, they could have carved through the hydrogen fog more quickly than stars alone. This raises a profound puzzle. How could black holes grow so quickly? The simplest black holes form from massive stars, perhaps dozens of solar masses. Yet Webb is finding evidence for black holes millions of solar masses only a few 100 million years later. That rapid growth either means they started larger than we thought, possibly collapsing directly from primordial gas clouds, or that early environments fed them at extraordinary rates. Each option pushes astrophysics into new territory. The story of reionization also reveals how structure spreads. Imagine the universe filled with foggy hydrogen. When the first galaxies switch on, they light small pockets around themselves, carving bubbles of transparency. At first, those bubbles are isolated, like street lamps in a thick mist. Over time, the bubbles expand and overlap until the fog clears. Webb helps us map the timing of this process by identifying when galaxies first appear and whether their light includes lines like Lyman alpha. If we see that line from a galaxy, it suggests the region around it was already cleared. By comparing many such detections, scientists are piecing together a patchwork map of Reionization. Observations so far suggest Reionization was not a smooth, uniform dawn. Instead, it unfolded unevenly across the sky. Some neighborhoods cleared earlier because they had clusters of active galaxies. Others lagged, remaining opaque for longer. This patchiness is consistent with simulations run on supercomputers, which model how gravity, radiation, and gas interact across millions of light years. Webb provides the data needed to calibrate those simulations. In a sense, every distant spectrum is both a measurement and a map coordinate, telling us how far the cosmic clearing had advanced at that moment. One subtlety often missed is the role of dust. Even at these early times, some galaxies show evidence of dust grains formed in supernova ejecta. Dust absorbs ultraviolet light and re-emits it in the infrared, too much dust, and a galaxy's contribution to reionization drops because its ultraviolet output is hidden. Webb's infrared instruments can spot this dust by looking at thermal signatures and spectral slopes. Surprisingly, dust appears earlier than expected in some galaxies, hinting that the first supernovae were already seeding the cosmos with complex chemistry. That chemistry would later be essential for forming planets, atmospheres, and ultimately life. Another emerging clue is the clustering of galaxies. Webb has found regions where multiple bright galaxies lie close together, suggesting early groupings or protoclusters. In such environments, overlapping bubbles of ionized gas would have accelerated the clearing of hydrogen. Clustering also indicates where the densest parts of the cosmic web were located, tracing back to fluctuations in the primordial universe. Each cluster is not just a set of galaxies, but a fossil of initial conditions laid down in the Big Bang. The practical challenge is distinguishing true high redshift galaxies from imposters. Some nearby galaxies filled with dust can mimic the red colors of distant ones. Webb's spectroscopy reduces that confusion by confirming distances, but it requires significant telescope time. That's why the initial surprise about impossibly massive galaxies has moderated. Some candidates turned out to be dusty, closer systems masquerading as ancient giants. This is not a failure, but a demonstration of how rigorous confirmation reshapes our picture. With each correction, the early census becomes more reliable. What emerges is a universe where small galaxies, acting collectively, likely provided most of the photons needed for reionization. Rather than a few titans, it was swarms of dwarfs that lit the way. That conclusion is striking because it mirrors how structure forms on larger scales, many small pieces merging over time into the giants we see today. The James Webb Space Telescope itself deserves a closer look because understanding its design helps explain why it can reach this far back in time. Webb carries a segmented primary mirror 6.5 meters across, made of 18 hexagonal pieces coated in gold to maximize infrared reflectivity. Unlike Hubble, which orbits Earth, Webb sits nearly 1 million miles away at a gravitational balance point called L2. At that distance, a massive sun shield the size of a tennis court blocks heat and light from the sun, Earth, and Moon. The telescope must remain cold, below 50 Kelvin, so its instruments can detect the faint infrared glow of galaxies billions of light-years away. 4 main instruments make this possible. NIRCam, the near-infrared camera, provides deep imaging across a wide range of filters. NIRSPEC, the near-infrared spectrograph, spreads light into spectra, allowing astronomers to measure redshifts and chemical compositions. MIRI, the mid-infrared instrument, extends coverage to longer wavelengths, crucial for detecting dust and cooler structures. Finally, FGS/NIRISS provides fine guidance and additional spectroscopy. Each instrument complements the others, creating a toolkit capable of catching ancient photons stretched by cosmic expansion. Why infrared? As light travels through an expanding universe, its wavelength stretches. Radiation that began as ultraviolet or visible billions of years ago arrives today as infrared. Only by building a telescope optimized for these wavelengths can astronomers detect the faint traces of cosmic dawn. Earlier missions like Spitzer confirmed the importance of infrared, but lacked Webb's resolution and collecting area. Where Spitzer saw vague smudges, Webb resolves structure and captures spectra. The difference is like comparing a shadowy outline with a detailed portrait. This leap in technology is why Webb can test theories that were once confined to computer models. For example, simulations predicted that galaxies at redshift 10 should be rare and faint. Yet Webb has already identified dozens of candidates, many confirmed with spectra. That result forces refinements to how quickly gas can cool, collapse, and ignite star formation in the early universe. It also provides direct constraints on dark matter because the growth of structure depends on how dark matter clumps. The faster galaxies appear, the more strongly dark matter must have seeded them. Crucially, Webb's deep fields are not isolated shots. They are part of coordinated surveys with names like CEERS, JADES, and COSMOSWEB. Each program targets different regions of the sky using multiple filters and exposure times. By pooling these observations, astronomers can build statistical samples rather than relying on a handful of anomalies. The consistency across surveys strengthens the case that early galaxy formation was both rapid and widespread. It also allows cross-checks against cosmic microwave background measurements, ensuring the narrative of Reionization fits both ends of the timeline. When viewers see a brilliant Webb image, it is easy to mistake beauty for decoration. But each color is chosen to represent specific infrared wavelengths, each dot of light carefully measured. These images are not just art, they are data maps of time itself. Every pixel is a history lesson, waiting to be decoded. One of Webb's most profound contributions has been sharpening our understanding of cosmic chemistry. The first stars contained only hydrogen and helium, the elements forged in the Big Bang. Everything heavier, carbon, oxygen, iron, had to be built later in stellar furnaces. Webb's infrared spectra can detect the fingerprints of these heavier elements even in the faintest galaxies. Already, researchers have identified oxygen in galaxies less than 500 million years old, proving that massive stars lived and died quickly, enriching their surroundings. This rapid enrichment has two major consequences. First, it sets the stage for planet formation much earlier than expected. While no planets could form directly from population 3 stars, their explosions seeded gas clouds with the raw materials for rocky worlds. Second, it complicates the picture of reionization. Heavy elements influence how gas cools, how dust forms, and how efficiently light escapes from galaxies. The balance between enrichment and transparency is delicate, and Webb's observations are revealing just how quickly the universe struck that balance. Black holes also factor into the chemistry story. As gas spirals into a feeding black hole, it heats to millions of degrees and produces characteristic emission lines. Webb has already spotted these signs in galaxies less than 1 billion years old. That means supermassive black holes were influencing their neighborhoods from the earliest times, shaping the flow of gas and possibly regulating star formation. Whether black holes suppress or stimulate star birth depends on conditions, and Webb is giving astronomers the data to test each case. A striking example is the discovery of candidate galaxies with broad emission lines indicative of active galactic nuclei. These signatures suggest that even while galaxies were furiously forming stars, some harbored central engines powerful enough to rival them in luminosity. The dual contribution of stars and black holes may explain why some regions of space cleared their hydrogen fog faster than others. Instead of a single mechanism, cosmic dawn likely featured multiple overlapping forces. It is also becoming clear that galaxies interacted earlier than once thought. Webb has captured close pairs and even merging systems at redshifts above 10. These encounters accelerate star formation by compressing gas and triggering bursts. They also promote the growth of larger galaxies through hierarchical merging. Seeing such interaction so early tells us that cosmic structure was dynamic from the beginning. The universe did not build patiently. It assembled in fits and starts, with collisions shaping the outcome. Through these details, Webb distinguishes evidence from hypothesis. The evidence is the spectra, the redshifts, the chemical lines. The hypotheses are the models that explain why galaxies look brighter, why black holes appear so early, or why enrichment progressed so quickly. Each new dataset narrows the field of possibilities. Reionization, galaxy growth, black holes, and chemistry all converge on a single theme: feedback. In astrophysics, feedback describes how one process alters its environment in ways that affect what comes next. Supernovae blow gas out of galaxies, regulating future star formation. Black holes emit radiation and jets that can heat or expel surrounding matter. Star formation itself can create winds that reshape a galaxy's structure. Webb's observations are revealing that feedback was vigorous at cosmic dawn. Consider a small galaxy forming its first cluster of massive stars. Within a few million years, the brightest of those stars explode as supernovae. The blasts push gas outward, creating turbulence and reducing the supply for new stars. Yet over time, gravity recollects some of that gas, leading to another burst. This cycle of burst, suppression, and renewal produces the bursty star formation pattern Webb is now detecting. It explains why galaxies appear brighter in snapshots than models predicted. They are caught during their fireworks phases. Feedback also shapes reionization. Ultraviolet photons from stars and black holes ionize hydrogen, but feedback-driven winds carve channels that help those photons escape. Without feedback, light might be trapped inside galaxies, and reionization would stall. With feedback, the fog clears faster. Webb's evidence of early Lyman alpha detections suggests these escape routes existed, implying feedback was efficient. Even on larger scales, feedback mattered. Galaxies clustered along the cosmic web, and their combined effects produced bubbles of ionized gas tens of millions of light-years wide. When these bubbles overlapped, reionization accelerated. Webb's ability to spot galaxies in groups confirms this pattern, grounding simulations in observation. What's remarkable is how quickly complexity emerged. Within a few 100 million years, the universe had already moved beyond simple hydrogen clouds. It hosted stars, supernovae, black holes, dust, mergers, and feedback cycles. Each of these phenomena leaves imprints in Webb's data. Lines in spectra, shapes of galaxies, brightness variations. By compiling these clues, astronomers reconstruct not just what happened, but how the interplay of processes sculpted the young cosmos. For viewers, the key takeaway is that the early universe was not static or slow. It was turbulent, dynamic, and surprisingly mature. That fact alone reshapes our mental image of cosmic dawn. What lies ahead is equally fascinating. Webb has only begun its mission, and many results are preliminary. Deeper surveys will extend the census of galaxies to even earlier times. Planned programs aim to detect galaxies at redshifts of 15 or more, corresponding to just 250 million years after the Big Bang. If such galaxies are confirmed, they will push the frontier of direct observation further than ever imagined. Meanwhile, other observatories will complement Webb. The Nancy Grace Roman Space Telescope, set to launch later this decade, will survey huge swaths of sky in infrared, identifying thousands of distant galaxies for Webb to follow up. On the ground, the extremely large telescope in Chile and the 30-meter telescope in Hawaii will collect high-resolution spectra, measuring motions, compositions, and structures of faint galaxies with unprecedented detail. Together, these instruments will create a multi-layered picture of cosmic dawn, from wide-field surveys to pinpoint analysis. Radio astronomy adds another dimension. Arrays like the Square Kilometer Array will map the distribution of neutral hydrogen directly, using the 21-centimeter line. These maps will show where the fog remained thick and where it had cleared, providing the missing half of the reionization story. By combining hydrogen maps with galaxy surveys, astronomers can correlate light sources with transparency, finally watching reionization unfold as a three-dimensional process. One of the most exciting prospects is detecting the first truly pristine stars. While Webb cannot resolve them individually, their deaths may leave distinctive signatures. A population 3 supernova would produce a unique chemical pattern lacking heavy elements. Detecting such a pattern would confirm decades of theory about the first generation of stars. It would also show us the raw materials from which all later complexity arose. Another target is the growth of black holes. Webb and its successors may catch galaxies where the balance tips clearly toward accretion rather than star formation. Understanding that transition will reveal how black holes reached millions or billions of solar masses so quickly. It may also solve the puzzle of why some galaxies shut down star formation while others kept building. Each new detection will refine timelines and test predictions. The process will take years, but every spectrum brings us closer to a coherent story of how light conquered darkness. Reflecting on what we have learned so far, it is remarkable how Webb has changed our perspective in less than 2 years of operation. Before, cosmic dawn was largely theoretical. Now it is populated with real galaxies, real spectra, and real surprises. The broad strokes of cosmology remain intact: dark matter, seeded structure, Gas collapsed, stars ignited, but the details, how fast, how bright, how complex, are far richer than anticipated. For the public, one distinguishing fact often overlooked is just how precise these measurements are. Redshift is not guessed. It is read from the positions of spectral lines with extraordinary accuracy. Chemical abundances are not hand-waving. They are ratios of emission strengths calibrated against models tested in nearby galaxies. Even dust content can be inferred from subtle slopes in infrared spectra. The rigor behind every conclusion separates genuine discovery from speculation. Another underappreciated insight is how these early galaxies connect directly to us. The carbon in your cells, the oxygen you breathe, the iron in your blood, all trace back to stars like those Webb now reveals. To say we are stardust is not metaphorical, it is literal, and Webb lets us watch the factories of that dust at work in the universe's first billion years. For those who wonder whether surprises undermine cosmology, the answer is no. Adjustments to models are not signs of failure, but of refinement. The core framework, the Big Bang, cosmic expansion, dark matter scaffolding, remains robust. Webb sharpens the picture, making it more detailed and more humanly tangible. It transforms abstract theory into direct evidence, visible in photons that traveled billions of years to reach our detectors. This is why each new release matters. They are not just pretty pictures, they are milestones in humanity's quest to understand its origins. And unlike many sciences, astronomy lets anyone participate visually. You do not need equations to feel awe when looking at a Webb deep field. But behind that awe is a scaffolding of evidence that makes the story trustworthy. As the curtain falls on this exploration of cosmic dawn, one thought lingers. Beginnings are never simple. The universe's first billion years were not a quiet rise from darkness, but a storm of light, gravity, and chemistry. Galaxies flickered into being. Stars lived and died in bursts. Black holes roared, and hydrogen fog yielded patch by patch. It was messy, chaotic, and yet profoundly creative. For Webb, each photon it captures is a messenger from that era. These photons crossed almost the entire history of the cosmos to reach us. They carry stories of stars long gone, of galaxies that merged, of black holes that once fed furiously. To read them is to hold a piece of time itself. And the story is unfinished. Webb is still in its early years. Roman, the giant ground telescopes, and the next generation of radio arrays are waiting. Each will peel back another layer, revealing more detail, more nuance, more wonder. If the past 2 years have already overturned expectations, the next decade will reshape the entire narrative of cosmic dawn. So what should we carry forward? Perhaps this: the universe is more inventive than we imagined. It makes galaxies faster, stars brighter, and black holes bolder than our models dared. Every time we think we understand its limits, it surprises us. That unpredictability is not a flaw, but a feature. It means discovery never ends. The closing image, then, is not resolution, but invitation. Imagine the night sky as a vast library where only the nearest shelves have been opened. Webb has unlocked a deeper aisle, showing us ancient books written in light. Countless more remain sealed, waiting for the right tools to unbind them. The journey is ongoing, and the next revelation may change how we see everything that followed. When you look up tonight, consider that the faintest light you see with your eyes is already thousands of years old. Webb teaches us that with the right tools, we can see billions of years further, all the way to when the first sparks turned on. And perhaps the greatest gift is knowing that every answer leads to another question, each one urging us to keep exploring.